Hello everyone, I'm Professor Harrison and welcome back to our module on probability for finance. Today we're going to be covering covariance, what it measures, how to calculate it directly from data, and a key limitation that ends up being just as important to understand as the number itself. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to the family fortune. Today he's starting to ask a question he should have asked much earlier. When Victor's fund was declining, were the rest of the estate's assets declining at the same time, or were those problems separate? He opens up another one of those mysterious letters. You already know how to measure the spread of a single random variable. Variance takes each outcome's deviation from the mean and squares it, and then averages across all the outcomes. That squaring step is what makes variance always positive, and it's what keeps the deviations from canceling each other out. Now we need a tool for two variables at once. Not just how spread out each one is, but how they move together. That's what covariance does. The covariance of two random variables, A and B, is the expected value of the product of their deviations from their respective means. For each observation, you take A's value minus the mean of A, multiply that by B's value minus the mean of B, and then average across those products. The result tells you whether the two variables tend to deviate in the same direction or in opposite directions, or without any consistent patterns at all. Before getting into the calculation, notice something about this formula. If you set both variables equal to the same thing, if A and B are identical, the product of the deviations becomes the squared deviation, and the average of squared deviations is just the variance. So covariance is a direct generalization of the variance. Variance is covariance with yourself. There's one more connection worth making before we work through the numbers. Back in the letter on variance, the rational quant showed you why the portfolio formula contains more than just the individual variance. For a two-asset portfolio, the variance of a combined position ends up including a term with the covariance of the two assets. And that term is what determines whether combining the two positions makes the portfolio more or less risky than holding each individual one. At the time, the covariance term was just there. Now we can actually calculate it. So let's work through it. Consider two equity holdings, holding A and holding B. Over 5 quarters, their returns look like this. Holding A came in at 3%, 5%, 6%, 7%, and then 9%, and holding B came in at 4, 2, 6, 5, and 8%. Step 1. Find the mean of each series. For holding A, those 5 returns averaged to 6%, and for holding B, they averaged to 5%. Step 2. Compute the deviation of each observation from its mean. For holding A, you subtract 6 from each return, quarter 1, -3, quarter 2, -1, and so on. And then for holding B, you subtract 5. Step 3. Multiply the paired deviations. The deviation of A in quarter 1 times the deviation of B in quarter 1, and so on for each quarter. So for quarter 1, we get -3 times -1, which is 3. Quarter 2, we do -1 times -3, which is 3, and so on. Step 4, we average those 5 products. They sum up to 15, and 15 divided by 5 is 3. The covariance of holding A and holding B is 3% squared. So what exactly does this number tell you? The covariance here is positive, and the sign is the most reliable thing about covariance. A positive covariance means that when holding A was above its average in quarters 4 and 5, holding B also tended to be above its average. And when holding A was below its average, so in quarters 1 and 2, holding B also tended to be below its average. They co-move in the same direction. A negative covariance would mean the opposite. When one variable is above its mean, the other tends to be below its mean. And covariance close to 0 means there's no consistent linear relationship. The deviations don't tend to point in the same direction or in the opposite directions. One common question is why we multiply the deviations rather than just adding them. The multiplication here is what lets the signs interact. A positive times a positive gives a positive product, both on average the same direction. And a negative times a negative also gives a positive product, both below average in the same direction. But a positive times a negative gives a negative product, making it so that you end up with a negative whenever things go in different directions. Adding the deviations directly would end up losing that information. Two negatives summed together would end up giving you a negative, and two positives summed together would end up giving you a positive, the two of which would end up canceling out despite the fact that they both represent the two assets moving together. So we can see that interpreting the sign of covariance is useful. The direction of co-movement is something you can read directly from the covariance. But the magnitude, 3% squared, is a different story. Is that a large covariance, a small one? It's honestly very hard to answer, and the reason is that the units of covariance depend on the units of both variables. So for example, we used percentage points when we were calculating the covariance of our two assets. If you had measured those using the same returns in decimal form instead, 0.03 instead of 3%, for example, the covariance would have come out to 0.0003. The same data, the same relationship, but you would get a different measure. If you were to do this using dollar price change instead of percentages, you again would get a different number. You'd even have a number in dollar squared units, which is very different from percentage squared. There's no way to compare a covariance of 3% to a covariance of, say, $15 squared and conclude anything about which relationship is stronger. This ends up being the main limitation of the raw covariance as a standalone measure. The direction is meaningful, but the magnitude doesn't have a fixed interpretable scale across different types of variables. So, if we ever want to compare two covariances, we need to make sure that we always have the same units across both of the covariances that we're comparing. This ends up being the main limitation of the raw covariance as a standalone measure. The direction is meaningful, but the magnitude doesn't really have a fixed interpretable scale. It changes with every pair of variables that you apply it to. The fix here is to divide the covariance by the standard deviations of both variables. That removes the units entirely and produces a number that always lands within a fixed range. That's the correlation coefficient, and that's what we're going to cover next. Danny sets down the letter. He's been treating two problems as if they were separate. Victor's fund losing money over the final years of his life, and everything else in the estate declining alongside it. He pulls Victor's records on the estate's remaining non-fund assets, real estate valuations, a small fixed income position, and lines them up against the fund's quarterly returns. He works through the rational quant steps, means, deviations, products. The covariance comes back positive, strongly positive. When Victor's fund was below its average, the estate's other assets were well below their averages too in the same quarters. When the fund was up, everything else tended to be up as well. They weren't two separate misfortunes arriving at the same time. They were the same misfortune, almost as if some hidden force was driving the value of the entire estate down at the same time. So that's covariance. It measures how two random variables tend to deviate from their respective means at the same time, whether they move together, move in opposite directions, or move without any consistent relationship. A positive covariance means co-movement in the same direction, and a negative covariance means opposite movement. And you compute it by averaging the products of the paired deviations across your observations. The sign tells you something real, but the magnitude ends up being scale dependent, which means you can't compare covariances across different pairs of variables without some additional steps.